All right, so this is video 6 for the behavioral analysis series, and I'm going to continue with the examples that we left off in video 5. So the two examples I left off was doing show the inf of the set 1 over n, where n's a natural number is equal to 0, and then show that the supremum of that set is 1. So first off, discuss, well, from a theorem in an earlier video, if you have some subset of the real numbers s that's bounded above, u equals the supremum of s if and only if s is less than or equal to u for all s and s. And then bullet point 2 is if v is less than u, there exists an s and s such that v is less than s. And the second thing from the theorem, u sup of s if and only if for all epsilon greater than 0, there exists an s and s such that u minus epsilon is less than s. Now this second one, that's called the analytical definition. And just to visualize, like, briefly before I go into the examples, let's say this is the real number line, and let's say my set S, let's say this is S. And so the first thing is, so u is going to be the supremum of that set. So let's say u is right there. Now notice everything in green is less than or equal to u. So all s is less than or equal to u. Now if there's a value v that's less than u, so let's say this v is right here, then there is some value s such that v is less than that value s. So any of the s's that are here are the values s where they're greater than that value v. So if v is less than u, exists in s such that v is less than s. All right, and that's these values in between. So that's that definition of supremum. Now the analytical definition. All right, so it says for all epsilon greater than 0, there exists an s such that u minus epsilon is less than s. So epsilon's any positive real number, and we take the difference. So let's say u minus epsilon puts this right here. And then there's essentially an interval of values. So all the s's that are right here are the values that are bigger than u minus epsilon. Okay, so that's that theorem. Now I didn't discuss this is the infimum analog to this. So the analog to this theorem dealing with the infimum is if you have a set that's bounded below, delta is the infimum if and only if delta is less than or equal to s for all s and s. So that just means delta is a lower bound. And then if delta is less than v, there exists an s and s such that s is less than v. And then the analog to the second bullet point from the supremum theorem delta is the infimum of S if and only if for all epsilon greater than 0, there exists an S and S such that S is less than delta plus epsilon. All right, and again, that's our analytical definition. So in the previous video, we had this theorem listed. This thing in pink or purple is the analog to that, dealing with the infimum. And recall an infimum is the greatest lower bound to the set. All right, so that's our value delta. Now delta is less than or equal to all values S and S. And then the second part was if delta is less than B, so let's say B is right here, then there exists an S and S such that S is less than B. All right, so that's all of these. And that's the visual representation of that. And then for the analytical, all right, so the analytical, if and only if, for any real number greater than 0, epsilon greater than 0, there exists an S such that S is less than the delta or infimum plus that real number epsilon. So let's say you add epsilon to delta, and you end up right here. This is delta plus epsilon. And then all of the values that are in this little interval right here are the values S that are greater than epsilon. Greater than. All right, so that's the infimum analog. Now, I just figured I'd go ahead and discuss that before going into the proofs. Now, there is a useful theorem that I'm going to use to do the proof for the infimum of the set being 0. And that theorem is if you have any real number R, or sorry, any real number A such that 0 is less than or equal to A, less than epsilon, for any real number epsilon greater than 0, then A has to be equal to 0. And so I did a proof for this, and it's a contradiction proof. And for the sake of contradiction, assume A is not 0. Well, since we're assuming, that means A has to be greater than 0, since we're not including the case that A is equal to 0. So therefore, and we know A has to be less than epsilon for any epsilon. So if we pick epsilon to be 1/2 times A, then we get A is less than 1/2 A, which is a contradiction. So therefore, A has to be 0. All right, so I'm going to use that in my proof. All right, so let's prove the infimum of this set is equal to 0. And the proof and I'm going to use the analog definition, this one. So let delta be the infimum. All right, and certainly delta is less than or equal to 1 over n for all n and n. All right, just because of what we're assuming as far as the definition of infimum. So it's a lower bound, right? That's a lower bound. So delta is less than or equal to 1 over n for all n. So that means we have delta as a lower bound. So now we just need to show that the infimum itself is 0. And we talked about the Archimedean principle and a corollary to the Archimedean principle. So I'll write that. Recall one of the corollaries to the Archimedean principle states that for all epsilon greater than 0, there exists a natural number n such that 1 over n is less than epsilon. All right, so using this corollary, there exists this n, where 1 over n is less than epsilon. Okay, and this 1 over n is an element of our set. We know delta is less than or equal to 1 over n. So then we have delta less than or equal to 1 over n less than epsilon. Well, by our theorem, there's a useful theorem. This is like our delta is like our value a. And so a has got to be equal to 0. So we have 0 is less than or equal to delta, which is less than or equal to 1 over n, which is less than epsilon. So we have 0 less than or equal to delta less than epsilon. So then delta has to equal 0 by that useful theorem. Okay, so that's it for the proof for that one. Now for the supremum. I'm going to use the analytical definition. Which states that U equals sup of some set S, if and only if, for all epsilon greater than 0, there exists an S and S. Such that 1 minus epsilon is less than S. Oh, sorry, U minus epsilon is less than S. All right, so that's what I'm going to use. All right, so for the proof, so I'm going to do this one a little bit differently than the the infimum proof. So notice 1 is greater than or equal to 1 over n for all natural numbers n. So that means 1 is an upper bound for our set. Now, for the analytical definition, so 1 is the supremum of the set if and only if for all epsilon greater than 0, there exists some element of our set such that 1 minus epsilon is less than that element. So 1 is also part of our set. Well, 1 is an element of our set 1 over n. Given epsilon greater than 0, there is some value in our set. So 1, our value 1 is such that 1 minus epsilon is less than 1. So I produced a value in the set such that the supremum minus the epsilon is less than that value. So therefore 1 is the supremum. All right, so 2 approaches I figured I'll show for these proofs. One of them I used the analytical approach, and the other one I made use of this theorem that was using the not the analytical approach, I guess, or analytical definition. So that's it for this video. In the next video, I'll do another example of a supremum or infimum example. And then from after that video, we'll move on to something else.